Uh, Welcome to this, the third and final keynote talk of this conference. It's a joint Mobile India COMSNETS keynote to be delivered by Dr. Venkat Padmanabhan. Venkat is principal researcher and the leader, the manager of the Systems, Mobility and Networking Group at Microsoft Research, a short walk from here. Venkat got his PhD from Berkeley. Spent, 9 years in Redmond, where at MSR in Redmond, also affiliated with the University of Washington Computer Science Department. So I've known Venkat since then. And now an equal amount of time here, right? Almost 10 years.
Almost, getting close, yeah.
Almost 10 years here in Bangalore. He is very well regarded and well known for his contributions to many areas of networking, both in core networks, wired, also wireless. Currently, his group looks at problems in white space access networks, video over wireless. Think of Skype, which Microsoft has. And as you can see from his talk, he promises to scare us about your smartphones. He's also on the advisory board of SIGCOM and has been a regular contributor and supporter to COMSNETS. I mentioned I've known Venkat for many years. I'm actually visiting his group, so it must be a sign of good taste that despite knowing me for so many years, he's invited me back here. He's also a fellow of the IEEE and of the Indian National Academy of Engineering. So without much further ado, let's welcome Venkat and listen to his talk. Thank you.
Thank you, Sumit. And I'd really like to thank the conference organizers for inviting me. It's really an honor. I've been, as Sumit said, been tracking this conference and been contributing in various ways, and it's really an honor to be giving a keynote talk here. So the title of my talk, as Sumit rightly pointed out, is something that might scare people. So that was not my intention. I made it up one day when I was asked to make up the title or send in the title. What I'm really going to talk about is something much more lighthearted. It's really about how smartphones and other smart devices can be used to sense things about humans, about people. And specifically, I'll talk about the work that my colleagues and I have done over the years and talk about the impact that work has had. So let me, one other thing, I would really like to make this interactive, so you don't have to hold on to your questions till the end. You can, if you have some questions, you can raise your hand. And also, at a couple of points in the middle, I'll try to pause and take questions. So let me actually start with a question. If you think of the world of computing, which I'm sure everyone here is very, very familiar with, what would you say is the most constrained resource in the world of computing? Any guesses? Battery, bandwidth, right? Power, yeah, so battery. Anything else? Time, yeah. That's a good answer. So there are things like CPU and storage and network and obviously battery and so on. All of them are constrained and you have to worry about them. But I would submit that they are not the most constrained resource because they all ride technology curves of various kinds. Some faster, some slower. Obviously CPU and things are because of, I guess, not because of, Moore's law has characterized the growth in CPU power. Battery, of course, is on a much shallower slope. In fact, Bob Broderson, who is a professor at Berkeley, long ago joked that the reason battery power cannot increase rapidly is that you have a lot of energy in a small volume. That's what's called a bomb, right? So, but the point is, as someone, a couple of people pointed out back there, what's constant and what's not changing is time, and particularly with regard to the human. The attention, the cognitive sort of cycle, so to say, a person has is fixed. Certain number of hours in a day is what you have, and so I would submit that in the long term, I mean, we would want to optimize for all of these metrics, but fundamentally the metric that you really need to optimize for is human attention, right? If you think of computing in the sort of larger scheme of things. And that's, again, here, so when you talk about human attention and what occupies human attention, there's a whole bunch of things, right? And this is obviously not an exhaustive list, but there is sort of what you read, who you're with, sort of the other people around you, that context. You think of your shopping context, sort of what you go and look at, what you buy, where you are. So if you think of a large mall or airport, your location in that place, your sort of commuting and sort of travel kind of things, and obviously, perhaps most importantly, your health, right? So how your body is feeling. And there are many other things. So there are all of these facets of human context that matter to people. And my thesis is that being able to track this context continually and with a view to sort of optimizing the human experience, time and other aspects, whether you do it individually for a person or you do it for a group of people or some combination, can be hugely beneficial, right? And I'll try to talk about that during this talk and talk about some of the technical work we have done to enable some of those things. And of course, there's a huge number of people now working in this general space, and there's a lot happening. And yeah, the thesis also is that then the emergence of smart devices, smartphones, and also other things like smart glasses and smart wristbands and so on, is a key enabler to accomplish that goal, right? So that's really what I'm going to talk about. So this is the sort of technology timeline that I will walk through. The point I should make is that these times I put here are really drawn from my involvement in this. It's not necessarily exactly when the technology emerged, but it's roughly along those lines. So I'll talk about what I would call the age of the pioneers. This is before my time, right? Before I even had a degree, I guess, the early 90s. And then around late 90s, while I was in Microsoft and Red Band, sort of the work we started, it was really in the sort of pre-smartphone and even pre-Wi-Fi era. Even 802.11b, the first popular standard, had not quite been standardized yet. And then we'll move to the emergence of smartphones, but smartphones that look like this, that had a keypad and no touch screen or anything, and no sensors really. The only sensor worth mentioning is the microphone, which every phone would have. What I've shown here is the sort of external accelerometer sensor that we paired with this smartphone using Bluetooth and so on. So and then of course, rapidly smartphones evolved into much more capable devices, many more sensors and so on. And then looking to the future, we have other kinds of smart devices, wearable devices coming up, right? So that's the technology timeline. And what I will talk about is three problem contexts. One is indoor localization, an area that my colleagues and I have worked in quite a bit. Talk about road and traffic monitoring, and this idea of physical analytics, especially in the context of retail. I'll talk about each of these three. And so the story is really a combination of the technology timeline and these problem areas that we have worked in, right? So start with indoor localization, then talk about traffic, go back to indoor localization, and then talk about finally physical analytics, right? And hopefully you will see the sort of some of the common threads that flow through all of these parts. Yeah, before I go on, I do want to acknowledge the huge contribution that my colleagues and collaborators have made over the years, whether by sort of directly working on some of the projects I'll talk about or just through their input and their feedback. I will call out some names when I talk about specific projects and papers later, but really without their support, none of this would have happened. So we'll start with what I call the age of the pioneers, and specifically in the context of this problem called indoor localization. How many of you are familiar with indoor localization or what that means? Okay, so it's a few people, but not everyone. So let me explain it. The idea is very simple. What you're trying to do is to locate a user in an indoor space, like a hotel like this, or a mall, or an airport, or some other place, right? Of course, when we say locate the user, we usually mean locate something that the user is carrying, some device, right? Because although of late people have been talking about even locating people themselves using reflections of radio waves from human bodies and so on, but for our purposes, it's really locating a mobile device that the user is carrying. And fundamentally, the reason I believe this is an important problem is that a lot happens indoors. Much of the world is outdoors, right? If you look at the built-up area in the world, it's probably a tiny fraction of the sort of total surface area of the Earth or whatever, right? But if you look at the time people spend, it is overwhelmingly indoors, and especially if you look at the commerce people do. the buying and the interactions and other things people do, it happens indoors. Like for example, this talk. So here the context is I'm giving a talk and you're in the audience. Let's say we wanted to capture that context. Well, GPS and sort of localization technologies built for the outdoors won't quite cut it. You need something for indoors, right? And this has been an active area of research in the mobile computing community at least since the early 90s, and I'll talk about some of the early work that was done. And in the recent years, commercial offerings have started appearing. In terms of applications, I kind of hinted at some already. So indoor navigation, so you're in an unfamiliar airport and you're rushing to your gate, you want to get directions, location-based advertising, and so on. And also this idea called physical analytics, which is about learning from the physical actions of users. And I will talk about this later on in my talk, so I will not spend time on it here. So the first obvious question would be, well, why not GPS? I mean, after all, the G in GPS is global. It's supposed to work everywhere. And it's a wonderful system, right? It's a, I mean, if you're not familiar, I'm sure many of you are, but it really is a satellite-based system. There's a constellation of 24 or more satellites that was put into orbit starting in the late 70s by the US. And so long as your receiver can see a certain number of satellites, it can get a location fix, right? Based on the principle of proliferation, although there are some details that I'll not get into. And the accuracy is pretty good, 10 meters typically, but you can do much better with refinements like differential GPS and so on, right? And other countries have started creating their own GPS-like systems, satellite-based navigation systems. The Russians with GLONASS, the Europeans with Galileo, the Chinese, and then India has also started launching its own. It's not called global, it's a regional navigation system, but a certain number of satellites will be in orbit. I think the first couple have already been launched. But if you look at indoor use, GPS has a few problems. Well, first of all, the signal that's coming from the satellite is extremely weak to begin with, right, well below the noise floor. And now if you're inside the structure here, it's pretty much impossible to get a lock onto that signal, right? So you really can't use that to get location. A second issue, and related to the fact that the signal is so weak, is that there's a lot of processing you need to do. So the GPS receiver typically consumes hundreds of milliwatts of power when it's active. And I'm sure many of us would have experienced it. If you leave your GPS on in your smartphone by mistake, or some application is running that's constantly using the GPS, your battery won't last very long. The third problem is multipath. So people have started building these sort of highly sensitive GPS receivers for indoors. But the issue is that even if you manage to get a lock onto the signal, chances are what you're seeing is not the direct signal from the satellite, but rather a reflection from some other building. So let's say, or some other structure. It could be a building 50 meters away. So if you look at this pseudo range, which is what is used for trilateration, it is inflated now by say 50 meters. And so your location fix has now got an error of the order of 50 meters, which, or I just said 50 meters, it could even be larger, which from the indoor localization viewpoint is pointless, because if you tell someone your location within 50 meters in an indoor space, that's not very useful, right? So for all of these reasons, GPS is not really a viable solution. And so the goal of researchers over the past 2.5 decades at least has been to come up with an accurate, low-cost, ubiquitous alternative to GPS that works out of the box. And actually that's an important point, the out-of-box thing. I didn't mention in the previous slide, but I'll explain it next. So let me explain each of these. So low-cost and ubiquitous is self-explanatory, and what that really translates into is we want to ideally be using existing infrastructure and existing devices for the purpose of doing indoor localization. We don't want to say, hey, you want to get indoor localization, buy this new device whose whole purpose in life is to locate you. Or worse still, roll out new infrastructure in this hotel whose only purpose is to locate people. You could do that if the value you get justifies it, but to first order, it is far easier to deploy a system like this if it didn't require new investment of that kind, either on the device side or infrastructure side. And that relates to both the low cost and the ubiquitous part, right? So if you can use existing infrastructure, and then you have a solution that could very rapidly become available everywhere because it doesn't require anything special, right? The out-of-the-box thing is actually a very important point, and GPS does extremely well here. The point here is that if you take a GPS receiver and turn it on anywhere in the world, right, in the middle of the Sahara, so long as it can see the requisite number of satellites, it can get you a location fix. even if you have never been to that place before and never done any calibration or any measurement there, right? So it just works out of the box. So really the requirement here is you want it to be calibration, your solution to be calibration free to the extent possible, and accuracy is obviously something that depends on the application, but you want it to be as accurate as your application requires. So that's turned out to be a very, very fertile area for researchers. People have loved the problem and they've essentially gone all over it and written, I've written thousands, probably it should be tens of thousands of papers written on this problem area with all kinds of very interesting solutions. And part of the reason for that explosion is that there's a whole range of sensing technologies you could use. Forget the algorithms that you use on top of this. Just the basic sensing technologies, there is infrared, there is RF, there is acoustic, inertial sensing, visual. There's a whole range of sensing technologies you could use. I mean, recently people are talking about barometer to figure out your, not exact location, but at least your altitude. So there's a whole bunch of things available. Now, let me talk about sort of one piece of work, which is perhaps the earliest piece of work in this space. And it's a system called Active Badge that was done at the University of Cambridge in the UK by a person called Andy Hopper and his team. And basically, it was based on diffuse IR. Right? So essentially, you used infrared signal to do location, and I'll explain how that worked. So the idea was the system had two components. There were these devices called the active badges that users would carry. Carry meaning they're sort of, think of it as your employee badge, but it's an active badge. What the active badge would do is it would emit an IR beacon with some periodicity. In the building or the space of interest, in the ceiling, you would have these detectors, the IR detectors, right? And to first order, the localization algorithm was very simple. If your badge is seen by a certain detector, well, you're in the vicinity of that detector. That's your location. So very simple idea, but it was, as I said, one of the pioneering ideas done in the early days and really received a lot of attention. And if you go back to our requirements, in terms of low cost, well, it requires this new device and so on, but then the point is that the IR sensor itself is relatively low cost, so it's not terrible from that viewpoint. It provided room level accuracy, which is good for many applications. You would like to know whether a user is in this lecture, because that's then their context is what's happening in this lecture room versus, let's say, something was happening in the next lecture room. It might be only 5 meters away, but then the context is very different. So the room level accuracy part was very useful. But the downside is it required the special purpose infrastructure. You need to have these ceiling mounted units everywhere. Of course, you also needed the badges, but in addition, you needed this. So you couldn't just walk into a new space and have this thing work without having installed those things. The room level coverage is a disadvantage also in that if you wanted to cover this room and the next room, you would necessarily require two ceiling mounted units. You couldn't have one sort of halfway between the two rooms and have it cover both, because IR is confined, just like visible light. In fact, it even doesn't pass through glass, right? So it basically is confined within the four walls of the room. I've listed room level accuracy also as a downside, because in some situations, in fact, it is. Think of a mall or an airport. Well, what's a room there? It's one huge open space. There's no confinement. And so you don't really get any useful location information using sort of a room level accuracy scheme. So that sort of is the sort of entry point into the work that my colleagues and I started in the late 1990s, where we said, okay, IR has got all these problems. How about RF? Right? We are all, I guess at that point it was not true, but we anticipated that RF signals, cellular or cellular was already there, but then wireless local area network based on RF would proliferate. Right? So you have RF signals, and you could try to use that for localization. And of course, GPS also is an RF-based system, and so you could do trilateration and triangulation and so on. But in an indoor environment, there's a lot of problems because of the multipath environment and the reflections and so on. Right? So the strongest signal you might be getting from an AP that's there actually could be coming that way, because the direct path is occluded. A reflected path actually is stronger than the direct path, and so your angle of arrival could be off. Right? So a lot of problems like that. So Victor Ball and I at Microsoft Research in Redmond, where I was then, started looking at this problem in the late 90s, and we came up with a very simple idea. Let's use the RF signal, but use it to fingerprint locations rather than to do trilateration or triangulation. And just to put this in context, when we started this project in 1998, as I mentioned, 802.11b, the first popular standard, had not quite been standardized yet. So the kind of hardware that was available then was pre-Wi-Fi, pre-802.11 hardware, like WaveLAN that was done by NCR, and then Digital created something called Digital Roamabout and so on. But we took a bet that RF-based wireless LAN seemed pretty interesting just from the viewpoint of providing connectivity. People would like to communicate. And so if we could piggyback a localization system on top of a communication system, then essentially for zero incremental cost, we could provide localization, because the deployment of wireless LANs would happen anyway because of the need for communication, right? And I guess we got lucky, and that turned out to be the case. And wireless LANs, of course, cover pretty much all indoor spaces of interest today. The idea, as I said, is very simple. Since we are all bathed in RF signals of various kinds, we could measure some aspect of that signal. The simplest would be just the received signal strength at a location, corresponding to signals from many different transmitters, and use that vector of measurements as a fingerprint of that location, right? So in the offline phase, you go to various known locations, shown as XY here, and measure the received signal strength from transmitter 1, transmitter 2, onto N, right? And that's the sort of the radio signal strength map that you create. And then in the online phase, when you're trying to locate a user, you just reverse this. What you do is you measure the signal strength and go into this table and see which entry of RSS values matches what you measured the best. And the corresponding known location is your XY, right? So that's the very simple idea. And that worked remarkably well. So we did various experiments in various buildings, and we found that median errors was under 3 meters. And we could bring that down even further with simple sort of averaging techniques and so on, right? So 2 to 3 meters is the kind of error we saw in the median. Compared to a naive scheme which simply said, oh, let me look at the point of attachment. Let me look at the access point to which my device is associated and use that location as the location fix. So we do much better than that. But of course, you'll notice that there is still a long tail. So we're talking about errors of the order of 25 or 30 meters in the tail here, which is unacceptable in many cases. So yeah, so before I talk about what we did about that, so in terms of the requirements are laid out, the fundamental benefit of the radar approach that we came up with was that it leveraged existing infrastructure. But I should not say existing, because when we did it, it was not existing. The then anticipated infrastructure rollout, right? Which meant, yeah, so that's a huge advantage. So both in terms of the infrastructure and the device, right? The device and the infrastructure both had what the radios that were necessary, so we didn't have to put in anything special. Because it worked with RF spectrum as opposed to IR, it could provide wide coverage. You could have an access point here and an access point somewhere else, and provide coverage to the entire floor, both in terms of connectivity and localization, right? You didn't need an RF device in every room to do this. And the accuracy, as we just saw, could be pretty good. The big problems were creating this RF signal map, right? This sort of upfront calibration effort is tedious. In fact, it is completely contrary to the out-of-the-box requirement and out-of-the-box attribute of GPS I mentioned. You couldn't use radar in this building unless you had come ahead of time, maybe employed some of the student volunteers, and actually mapped out the entire floor, right? So that's a big disadvantage. And that is compounded by the fact that the RF environment can change. Think of a mall, let's say. Okay? Let's say you employ the janitors and make the measurement in the middle of the night when the mall is empty. You're really trying to locate people when the mall is full, let's say. The RF environment could be very different. And so the measurements you made in the middle of the night wouldn't quite carry over. And as we just saw, the errors can sometimes be very large. So in radar, we do look at various ways of improving this using modeling, using a technique called environment profiling, where we took advantage of the fact that the access points themselves are fixed nodes. And so if you made measurements between the access points, any change in those measurements of, say, received signal strength could only be attributed to change in the environment because the location of those devices is not changing. The access point A is here, B is there. So we could use those kind of measurements to index into a table of RF maps and pick the right RF map. So I'm not spending too much time here, but if you're interested, I can point you to papers or talk to you offline. We also did continuous user tracking. So the idea there is, because of aliasing and sort of multipath and so on, you might not quite be sure where whether the user's location is here or there, because two different locations could look very similar when you measure the received signal strength. But if you measured the user continuously, user location continuously, you can often disambiguate between these two, because the simple observation is that it's very unlikely the user will be here one moment, there the next moment, back here the third moment, and so on, right? So you could use the continuity of physical motion to improve error. So we did all of these. We wrote a paper and also filed for some patents. And then, let me pause that. I will come back to interlocalization. We're not done yet. Yeah, Samir. Yeah, but the thing is that for citing of APs, you're trying to get coverage. Here we are doing more than coverage. We need to know what the RSSI was, right? They'll create a map. So I think the modeling thing that I talked about here is kind of trying to do that. So essentially build an approximation. You give up some on accuracy and so on. Yes. But the thing is, it's still effort, and the complexities of a given indoor space can be substantial depending on and also the access point can sometimes move. I mean, there are a lot of other things that can happen, right? So anyway, so I'm going to pause indoor localization. We're not done with it yet. We will come back to it because I'm following the storyline that I talked about, and we are going to now jump ahead several years to the emergence of smartphones, right? Of course, in the intervening years, I was doing other things, other projects, other stuff, which I'm not talking about here. Now, on a personal level, what happened at this time also is that I moved to a very different world. I was working in Microsoft Research Redmond, as Sumit mentioned, and then I moved to Microsoft Research here in Bangalore in 2007. But aside from the 10,000 miles that I traveled, I moved from a world that looked like that, or during busy hour that looked like that, to one that looked like this. And what you will see about that picture, and it's of course to this audience is extremely familiar. Sometimes when you give a talk to an audience that's unfamiliar, it is a revelation to them. I mean, no two vehicles look the same, and no two are pointed the same way, right? It's no audio. Anyway, so this is a video clip from 2007. I get to give talks in the US and so on to just give people a feel for what we are talking about here, right? And you talk to a lot of visitors to Bangalore for the first time. The first thing that hits them, quite literally, is traffic. Right? That's what they really notice is different. And what you see is, in general, the road quality can be very variable, potholes and so on. There's a lot of braking, honking, different kinds of vehicles, and in general, a lot of chaos. So up to that point, if you looked at the work people did well, I mean, this audience doesn't require it, yeah. But so there's a lot of work on traffic and so on that was based on GPS tracking. The idea was, hey, we'll track the vehicle using GPS, and we know where it's going, and we know the speed and all that, right? We know congestion. But there's a whole other dimension or other dimensions to traffic and road conditions in a place like India and a lot of other developing countries that is not within the realm of GPS, right? And so the question we asked ourselves was, hey, these smartphones are emerging. Can we use them to measure these conditions in some meaningful way and then maybe use that to do something with it, right? So what we did was, okay, we took what was perhaps among the leading edge smartphones then, an HP, HP iPac. And as I mentioned, it didn't have any sensors. So we took an external accelerometer sensor, and that coin, the size relative to the coin tells you how large it was. Today it will be one single chip that's embedded in your smartphone. and we just paired them with Bluetooth, right? So that was our accelerometer enhanced smartphone in 2007. And we sort of set about using this. So there were a whole bunch of interesting problems we had to deal with, one of which was the energy challenge, right? So if you look at these sensors on, again, this is all measurements for the iPack. The energy consumption of GPS or even sort of using the microphone is of the order of hundreds of milliwatts. On the other hand, the accelerometer sensor itself is only 2 milliwatts. Of course, to process the accelerometer data, we did need to burn the CPU cycles. But of course, these days, there are dedicated low-power sensor processors that allow you to do continuous processing. But fundamentally, the sensor itself was low energy. So we came up with this very simple idea of triggered sensing. So there's a lot happening on the road. Let's use a cheap sensor and run it continuously and make an approximate guess of what's going on, and at the appropriate time, trigger the more expensive sensor to make more accurate measurements, whether it's GPS or microphone or something, right? So that, and there's a whole bunch of examples of things we did. Let me just sort of talk about the last one here, localization. So you could use your existing cellular radio, GSM radio, or, and cell towers to get an approximate idea of your location within a few hundred meters. So if you're trying to monitor, you're trying to map out potholes in the central business district of Bangalore, and your cellular information tells you that you're at the airport or you're in another city, there's no need to be using your GPS and burning energy. You can turn on GPS when you're within the sort of radius of interest, for example, right? So that's a very simple idea. So there's a whole bunch of other examples. And another technical problem we had is this problem of what I call as disorientation. So the idea is the following. Let's say you're in a vehicle and you draw the 3 axes. You have the x-axis pointed toward the front, the y-axis pointed, let's say, to one side, and the z-axis pointed to the ground. And let's say you're trying to detect braking and sort of the braking behavior, right? The obvious thing is, okay, I mean, the braking signal will largely be manifested along the x-axis because that's where the velocity is changing, right? The z and y should not change. But the problem is that the device you're using to make the measurement is your smartphone, which is at some arbitrary orientation relative to the vehicle. It could be in your pocket, in your bag, on your dashboard, in some arbitrary orientation. So you have this little x, y, and z, which are the axes of the device, which are not aligned with the capital X, Y, and Z. So when you do braking, what you would expect, as I said, is a strong signal along the X axis, which is shown by the red color here, and nothing much on the blue or the green. But what you might measure is something that looks like this, where there is something on the green, something on the red, something on the blue, so it's all a mixture, right? And so you need to do an alignment of these two. So the question is, how do you do that? So we again had this idea of triggered sensing for this. So basically the idea is there are basically 2 force fields that we take advantage of. One is gravity. Okay, gravity is always acting with a certain force on the device. So actually another question. So let's say I have my smartphone and it's lying flat like this. The z-axis is pointed to the ground. What would the z-axis accelerometer reading be? Any guesses? Let's say the smartphone is just on the table. What would the accelerometer reading along the z-axis be? Okay, who said that? Okay, good. I didn't expect that answer. I thought people would say 0 because the thing is not moving. But in fact, these are what are called DC accelerometers, which are measuring the force on the mechanism of the accelerometer. So it will give you 1 G as the reading, even when nothing's happening, which is good for us because that gives us one known force field, which we can use for the purpose of orientation. But that's not sufficient because any rotation about the vertical axis will still be consistent with that one force field. So you need a second force field. And that's where we took advantage of braking to do orientation. So the idea is that when braking happens, you will expect a temporary force field along the capital X axis. And so if you could use a different sensor like GPS to detect braking just by change in velocity, then simultaneously you can say, okay, I know braking is happening because GPS tells me braking is happening. Let's see what the accelerometer is doing and align it in a way such that the two force fields are gravity and an acceleration or deceleration along the x-axis. So that's basically, there's a little bit of math here which I'm not going to talk about. We did that, and we were able to align this with no human input in a way such that it matches the picture that you want to see, right? Which is that when there's braking. So once you have oriented your device, you can now start using it for all kinds of things. You could detect road bumps by, now you know which way Z is, so you could sort of look at the accelerometer signal along the z-axis. You could, let me skip this. Basically, so we did this, and then we sort of aggregated information from bumps in an energy efficient way. We also had this interesting problem of, let's say you have congestion. There is stop and go traffic versus a pedestrian who's walking on the side. How do you tell the two apart, right? You don't want to take information that's coming from a pedestrian's phone on the sidewalk and mistakenly think that there is so much congestion that there is stop and go traffic on that roadway, or vice versa. Again, the accelerometer can help here, because if you look at although the velocity in both cases is the same, the accelerometer signature is very different. Here you see the periodicity of walking, whereas in the stop and go, in an accelerometer that's in a vehicle that's stuck in stop and go traffic, you don't see that. So we are able to tell these apart. We also looked at using the microphone to detect honking, and I'll not talk about this, but basically you take advantage of the fact that it's basically the microphone on your phone is obviously designed to work well in the range of frequencies that the human puts out, right? Well, not coincidentally, but I mean, it's sort of as a consequence also, the sound signal put out by a honk is in the range that a human can hear. So they're nicely aligned. So you could use your microphone and actually pick out the honk quite nicely. So we did this. We did a small scale deployment using shuttles and sort of MSR India and so on. So about 5 or 6 of them, and we gathered some data and did that. We wrote a paper and we put out tech report, and then then this happened. One fine day in July of 2008, we got an email, and Ram know this. Ram is also here, from an Israeli company. Essentially, it was a legal notice saying, "Hey, you called your system traffic sense. Stop that, because it is our trademark, and you guys are not supposed to use this." And our paper was about detecting road bumps and so on, and perhaps to rub in that point, they said, "We bumped into your paper, and stop using this," right? So immediately we considered our lawyers, and we, Prashant Mohan was our student, and Ram and I, all three of us Tamilian. So we said, okay, we'll pick a Tamil word, nerisal, which means crowding or congestion. No Israeli company would have chosen that, and perhaps no other company either. And so that's the paper we wrote. And that's turned into an area that's really picked up. A lot of work at MIT and Princeton and IIT Bombay. I guess Riju Rekha and Bhaskar are not here, but they did a lot of nice work on road and traffic monitoring. And it continues. I mean, I think there is, in the end, I'll come back to this. There is a lot that has been done and can be done in this space of using devices to measure traffic and road and things like that. Now, I also wrote to a few colleagues and working on various areas overlapping with what I was going to talk about, and they were kind enough to send me a slide on their work. So this is a very interesting body of work done by Professor Peter Handel at KTH in Sweden, where his team is looking at smartphone-based sensing as an input into insurance. Right? Without getting into too much detail, if you look at this chart here, what they're saying is they're looking at sort of various metrics like how much braking is happening and how much, they don't have honking because I guess it was done in Sweden, so they didn't have that, but they have braking and cornering and swerving and all that. And they talked about how relevant it is from an insurance viewpoint, which metrics correlate well with risk and which ones are less important. Right? So this is one application of using this kind of sensing in a sort of commercial setting. I also got something from Ramon Caceres, who's now at Google, but who did all of this work while he was at AT&T Research in the US. This is a very different kind of work, less related to what I talked about, but again, it's about traffic and using phones to measure things. So AT&T obviously is this big operator, so they sit on the infrastructure side and they're able to monitor locations of the phones in their network, right? And so what they could do, for example, is by looking at the location during the middle of the day versus middle of the night, they can figure out where the user's home is and where their workplace is. And then what they did was they did a carbon footprint analysis to say, okay, this is a map of the New York, New Jersey area in the US. I mean, if you're not familiar with it, it doesn't matter, but the point is that these little enclosed regions represent density. So the smaller they get, the denser the region is. So this is like Manhattan. This is the sort of perhaps the densest area. And the further away you get, the regions get larger and it's less dense. And they're plotting the carbon footprint. So how far people commute to get to their workplace. And the greener it is, the better it is, the shorter the commute. And you see the expected pattern. The outlying areas are less green and the sort of things around Manhattan are more green because people have to travel less there. But they also did this in a few other cities. So this is San Francisco, and the pattern here is actually a little different. In this case, yes, some outlying areas up in the north and south are red, but there are some things that are quite far out this way are still quite green. Maybe the folks there work locally. I mean, we don't know. So anyway, the point here is that smart devices, and I guess in this case just phones, can give you a lot of interesting data about what humans are doing and whether individually, as I said, or in this case, more collectively, right? So you could plan your city or you can plan your next green initiative depending on this data. So with this, I'm going to conclude this part, and if there are any questions, I'll take them now, and then I'll switch back to indoors. Yeah.
Another kind of paradigm, like the base story of crowdsourcing is another
Yeah.
way of trying to do this thing.
Yeah. So the joke that Ram and I and a few others have is that we have had a few ideas that other people have turned into billion-dollar ideas, right? So when we started this, our goal was to exactly do this, right? Put this in phones and have it scale. But I showed you the struggle we had with even getting a smartphone that had the necessary sensors, right? I think if we had done this a few years later or continued it, we could have pushed in that way. Of course, to give a lot of credit to Waze, they scale it up to hundreds of millions of users. It's not easy, right? So I think that's really, crowdsourcing was exactly the model. In fact, we did I'm not going to talk about it, a sister piece of work called Prism, which is a software platform for enabling exactly that kind of crowdsourcing thing. So you run Prism on your device and jobs would come and they would execute on your device and all of the management would be taken care of by Prism. Right? Of course, Prism is also a bad word, I guess, these days, isn't it? Is that the NSA system that's listening on people? So we should not talk about that. Anyway, any other questions? Yeah.
What will it take to get a transit map for Bangalore like this?
To get a map like this today, I would say it is relatively easy. I mean, in fact, I've been talking to a few people, including to Bhaskar Raman, about doing some of this stuff. Yeah, because today people have devices in their pockets that are capable. They have all the sensors. Yeah, it's something. I mean, see, traffic level things people are already doing. There are commercial services that are providing. But if you wanted this more detailed pothole mapping and other kinds of sensing, some of these ideas and work that other people have done could easily be packaged into a piece of software that goes into a device that is in your pocket. So if that's something of interest, certainly be happy to talk offline. Okay, so let me move on. Let's head back indoors. Remember I talked about radar and all that stuff. And then we're coming back. But now we're coming back 10 years later, to 1998 and now 2009. And whereas the mobile devices then were laptops and there was, as I said, it was pre-Wi-Fi era and so on. Now we are talking about very capable smartphones. Of course, being from Microsoft, I put a Windows phone there, but frankly, the pioneer here was really iPhone and sort of Apple with its iPhone. Device with lots of sensors, including the accelerometer and compass and other things. And of course, it's programmable. So let's go back to radar. So what happened in the 10 years that I was doing other things was that this paper we wrote somehow caught the attention of a lot of people and garnered thousands of citations. I mean, this is the count today, but even back in 2009, I think it was a few thousand citations, which was, I guess, a pleasant surprise. We didn't quite expect that. But if you look at the work that was done, much of it was very nice work on improving accuracy and robustness. Right? So we had this very simple fingerprinting and matching thing. So people came up with probabilistic matching instead of some deterministic matching. Looking at, instead of absolute signal strengths, looking at relative signal strengths, adding some map-based constraints, a whole bunch of things. Right? Lots of work. Very nice work. The other thing that happened is that this is more recent. As I said, commercial services have been rolled out. There are various large and small companies that have been rolling out services, and in many cases either they explicitly say so or it's speculated that it's all based on RF fingerprinting or Wi-Fi signals. So the same basic principle that we laid out on radar is what is being used, simply because that's the source of signal that is readily available. Wi-Fi is everywhere indoors today. And also recently a colleague pointed out to me that Microsoft obviously makes Windows Phone and so on, but we actually make quite a bit of money from Android as well, because there is a bunch of patents that Microsoft holds that are licensed out to Android people. And in that list that came out was one of our radar patents as well. So that's one of the, 30 or 50 patents that Microsoft licenses to Android folks, right? So all of that is nice, but going back to the problem I mentioned earlier, this whole idea of doing a survey and calibration is tedious, right? You have to you don't have to walk exactly in a grid like this, but you have to go to lots of places depending on the accuracy you want and measure signal. And as I said, it can change between daytime and nighttime depending on crowding. And so that's expensive and tiring, right? I mean, it's sort of tedious. So the goal of our more recent work was to see what we could do about this. And as I said, what's changed is now that we have smartphones in everyone's pockets, we could potentially crowdsource information. So let's look at this here. This is actually a mock-up of the MSR India floor. And let's say the user walked from point A to point B along a certain path. Now you don't know that. They walked from A to B. Okay? If there is software running on their smartphone, that software could easily be doing Wi-Fi scans, right? It could basically scan, it could measure the signal strength from 4 different access points at various times with some periodicity. So you can easily generate lots of data, no problem. And you have 50 people here or 100 people here, even more data can be generated. But what's missing is the ground truth on location. Remember in radar, we were essentially taking a known XY and measuring signal strength. So that was the table we were creating. Here we don't know where the measurements were made. We can generate a lot of data, but we have no clue of which location those measurements were made. So we need to do something more, right? So essentially we need to do one of two things, or maybe both of them. We need to reduce dependence on ground truth, so work with fewer known points, and or come up with an alternative way of establishing the ground truth. And we did both of these. A piece of work called Easy with Krishna Chintalapudi. I don't think he's here. He's a colleague of mine, along with a student who's now at Berkeley, Anand Iyer, where we used some interesting modeling techniques to reduce the need for ground truth. I will not talk about that here. I'll talk briefly about the second part, which is to take advantage of these new inertial sensors like the accelerometer and the compass and so on, to establish ground truth in an alternative way. When I say alternative, I'm referring really to what happens in the outdoors. So there's a notion of war driving, where you basically go out there and sort of measure Wi-Fi signals, and you take advantage of GPS to get you ground truth. That works outdoors. But indoors, as I already discussed, GPS doesn't work, and so you need an alternative. So that's really what we did in Z, and I'll briefly talk about that. So the idea in Z was to enable zero-effort crowdsourcing of such Wi-Fi measurements. The idea was once you've got all these Wi-Fi measurements, where you have Wi-Fi measurement coupled with quote-unquote known location, you could feed that into radar, you could feed it into some other modeling technique and get a localization system going, right? Now, there's a lot of work in this general space, but doesn't quite carry over. I mean, the robotics people have been working on robot tracking for a few decades, using inertial sensing as well as other more fancy sensing like laser rangefinders and so on and so forth, right? But the big difference is that whereas a robot often moves on wheels, and you can have wheel odometry and measurements like that, here we are talking about using a human who happens to be carrying a device to make measurements. right? People walk, they don't move on wheels. And not just that, the way they walk depends on the person. I mean, if you're someone like Giri and you're 6 foot plus, you take 10 steps, that represents perhaps a much longer distance than someone who's 5 foot tall, right? The second thing is that a lot of work has relied on careful placement, pedometers, you have a foot-mounted sensor or something that has to be on a belt clip and so on. Here we're talking about someone's smartphone. We're using someone's smartphone to make measurements. You can't tell them, hey, thou shalt wear your smartphone on your belt clip at a certain angle. You can't do that. So you have to basically deal with the fact that the placement of the device is arbitrary. And there's also been work that's relied on user input. The user says, hey, I'm here, and now please track me. Which is okay in some situations perhaps, but humans are terrible at giving input. They are wrong, plus it's sort of burden on them to ask for input. So our goal was literally to go zero effort, no input, arbitrary placement, and obviously no wheels on people's legs, right? And so I will not talk about all of this, but basically we solved a few problems. We came up with a way to do placement independent step counting, a way to do stride length estimation, a way to estimate the heading offset. So you might think, hey, there's a compass on the device, so I know which direction the user is going. No. The compass just tells you which way the device is pointed. This compass, let's say the compass says, oh, I'm pointed towards north, but I could be walking this way. I'm walking at an angle that is offset relative to which way the device is pointed, right? And that's arbitrary. So let me just illustrate one of these problems, the stride length estimation, where we use this idea that we call as map-based constraining. So the idea here is, for an indoor space like a mall or an airport, I have a map that tells me the layout of the space. And I will use that to do a few things, including stride length estimation. So let's go back to this picture we had, which is the MSR India floor map and the walk from A to B. So remember, the user walked from A to B, and I pointed out we could make the Wi-Fi measurements, but we didn't have a clue where the measurements were made. So we used a technique called particle filtering, which is well established in the AI community, but then we augmented it in a few ways to solve this problem. So since you don't know where the user is, you just make guesses of where the user could be, and that's everywhere now. So all the open space, except the offices, all the hallways and so on, are filled with what are called particles. Particles are nothing but samples from a probability distribution. In this case, the probability distribution is very flat and it covers the entire space because we don't know, we don't have any information. You don't know the initial position, you don't know the stride length. In this case, we assume the orientation is known, but we can deal with that as well. And so we have initialized particles across the floor, and then as you detect steps and you detect turns using your gyroscope and compass, you evolve these particles. So the idea is that as the user starts walking, if the users in fact started from there, then 1 step later they would be here, 2 steps later. If the user in fact started from there, 1 step later they would be here, 2 steps there. So you keep evolving your guesses. And then you apply the simple constraint that people cannot walk through walls. That's where the map-based constraining comes. The map imposes some constraints that tells you where users can go and where they can't go. And so you see that many particles get eliminated because they started with an incorrect hypothesis, because that hypothesis led the particle to walk through a wall, which cannot be done by human. And so in the end, you are left with a fairly compact clump of particles, which is your guess of where the user is. And once you have sort of figured out where the user is in the end, you know that those are the only surviving particles. You can go back in time and figure out where the user must have been. Take those Wi-Fi scans, okay, and this here. So we did that. Alongside this, we also estimated stride length. So that's the other dimension of those particles, which is not shown visibly. And so we were able to estimate the user stride length, starting with a wide distribution and narrowing down. So we did all that, and how will this work? So this has actually been tried by some of our partners in Microsoft in Redmond, in a few malls in Redmond, but this is a large mall in the Seattle area, where I show a walk. This is the ground truth, a 1.2 kilometer long walk through the mall, right? If we didn't use Z and simply used the sensors and did some integration and all those things, this is what you get. Pretty soon, your estimate of the user is way outside the mall. And that's because of all the errors that you accumulate with the compass and so on. Whereas if you use Z, we get something that's pretty good, right? So it just shows that the map-based constraining and the other algorithms in Z worked quite well. So now I'll come to the last part and keep this quick. In recent years, of course, people have been looking at what's beyond the smartphone. And wearable devices is what's being talked about quite a bit. And there are wearable eyewear devices, Google Glass being the most well-known one, but there's many other wearable eyewear devices as well. And so in that sort of context, we are sort of looking at what we call as physical analytics. Right? The idea here is that in the online world, you look at an Amazon or a Flipkart, they do a great job of measuring a user's activity on their website. Even if the user doesn't make a purchase, they know that people who clicked on this product, they also clicked on that product, and they came back to this product. They know exactly what the user did. But think of a large store today. You might go to the store and pick out a lot of things from the shelf, put them back, come back 3 times to the same shelf, and then walk out without having bought anything, and the store gets zero information about what you did. But in fact, there's a lot of information that could be used to optimize the human experience and, of course, the store's business as well that's available, and that's really what we're after in physical analytics. We want to essentially treat the footsteps as equivalent of clicks online, right? And that's really what we're trying to do. And before I talk about wearable, let me talk about what we can do with the technologies I've already talked about, indoor localization. This is again in our floor in MSR India. We had a demo session, and we used indoor localization to create a heat map of where people were. And we clustered it, and we have this cluster here, which is very, very red. Any quick guesses on what demo this corresponded to? There were a whole bunch of 20 demos being shown. This demo here was very popular. Any guess what it might be? I'm sorry? Wonderful, yeah. Food. The food was being served there, and that was very popular. But then that's showing the number of unique visitors. If you weight it by time spent, actually the right thing happened. Food is no longer very hot. So people picked up their snack and did the right thing. They went and saw the demo. Right? So you could do analysis like this using indoor localization to do physical analytics. In this context, Archon, who's sitting back there, was kind enough to send me a slide on some of the very interesting work that they're doing in Singapore on a system called Groomon. They're doing a lot of other things as well, but I just picked out this one. This is about group detection. Right? So one of the things that's different about the physical world compared to online is that your human context of who's around you and who you're with matters, even from a shopping context. Right? See, when you're on Amazon website and clicking, you're the only person clicking. Right? When you go to a store, and if you're a couple versus you're a family versus you're a single person or a group of teenagers, your context is very different. What you might do and what you might be interested in at that time could be very different. So they built a very nice system to do this, and in the interest of time, I'll just, I think I give you the high level gist. So there's a trade-off between accuracy and how quickly you can detect groups and so on. So if you're interested, you should look at their census paper that appeared just a couple of months ago. Finally, and I'll just take 2 minutes. For physical analytics, I really think looking beyond the smartphone can open up new vistas. And the particular thing we have looked at is smart glasses. And we have built a system called Third Eye. Third Eye because there's the camera that's looking at what you're looking at. And we did tracking of retail behavior. And let me really jump to this thing. Essentially, we try to classify a user's behavior into walking, just walking through a store, dwelling at particular sections, gazing at particular products, and perhaps reaching out for certain products. So in some sense, you can think of it as sorted in increasing order of interest that a user is showing. And we did this, and we wrote a paper. But rather than talk about this, what I need audio, please. Audio on, yeah. I will show a nice video that Aishwarya Ganeshan, this is work with Aishwarya and Krishna, I already mentioned, and Lily Chu and at UT Austin, one of her students who was an intern. Aishwarya put together a very nice video that shows the system in operation. In fact, she demoed it here downstairs, I think, last 2 days. Yeah, let me, sorry.
Consider a typical retail store scenario. A user enters a retail store and she might walk purposefully to a section that she has in her mind. Upon reaching that section, she might dwell in that section, browsing through the aisle looking for products to buy. While dwelling, She might gaze at specific products or examine them more closely to determine whether or not to buy them. Each of these physical aspects of the user's shopping behavior might be indicative of her interest. Tracking the elements of physical browsing like walking, gazing, dwelling, reaching out, etc. might give us deep insights into users' interest. We term this physical analytics. For this demo, we have created a mock-up of a retail store, and let's now see how our system Third Eye helps us in tracking users' physical browsing.
At the top, it shows what the system has detected. It's detected that you're looking at this thing called baggeries. That's the item. See the transitions between walking, dwelling, and gazing. Because shoppers don't quite look like this today, but you never know how technology might evolve.
We can perform analytics on the data gathered using our system and draw conclusions like which is the product that was viewed the most. Apart from retail stores, our system can be used to track users' physical browsing in other indoor spaces, say during a conference or a trade show.
Okay, this is my last slide. So I hope I've convinced you, or at least made the case that smart devices, including smartphones, are a very powerful source of signal about humans and can be quite transformative in what they enable. And what I want to leave you with is a challenge. Can we use these devices to actually pick up some really meaningful societal challenges in India or in developing regions in general, and actually make a measurable difference there? And I've listed a couple of them here. With regard to traffic, safety is a huge issue, right? I looked at some statistics, 1.24 million road fatalities per year across the world, of which 20% are in India. I have the Bangladesh number here because I gave the same talk in Dhaka a few days ago. And can we use devices to make driving safer, make vehicles safer, and so on? I think there are some ideas that I've been talking to some people about. I'd be happy to talk to you as well. The second is thinking of these sort of wearable eyeglass devices. Can we help the visually impaired people see in some form? Right? And I think the key here is coming up with low-cost solutions that are also effective. And if you can have that combination, you can scale. Thank you.
In the interest of time, maybe a couple of quick questions for Venkat.
Yeah.
Commission has mandated location accuracy in indoor, including the vertical heights for enhanced 911 service. So do you think that these kind of things will help promoting a policy of providing good location accuracy for emergency services?
Using mandating location capability, would it? Right. No, I think, yeah, I think it's a step in the right direction, because clearly for emergencies, as you mentioned, it is important to know where people are. And but I think beyond that, beyond such mandates, even from a commercial viewpoint, there is enough reason to locate. In fact, there are a lot of startups now looking at tracking people in stores and figuring out, so doing some of the sort of analytics I talked about. So the kind of mandate from organizations like FCC can just provide more impetus, but even otherwise, I think things are happening. Yeah.
So from a user's perspective, what is my motivation in enabling the app that will help me myself being tracked? I would be concerned about privacy issues. I would be concerned about
Yeah. So I think if we go to the last thing, I talked about this glass, right? We talked about analytics, where you're gathering data from multiple people and doing all those things. But that's not the only thing. In fact, the primary thing would be to provide value to the user. So it's like, let's say you went to 2 different stores and you browsed at certain products, you didn't buy them. When you come online, if you had that context, you could directly go to the web page of that thing, or you could get related products. Essentially, think of it as something that's measuring your, recording your context across the physical world and the online world in a seamless way. Whether you, in addition, share it in some form with other people and allow aggregation, that's a separate question. And I think it would make sense in some situations. But privacy is an important issue, but it's kind of orthogonal to the basic technology that we are talking about here.
Okay. In the interest of time, let's thank Venkat once again. There's a small memento on behalf of COMSNETS. Venkat.
Thank you.
This is from Mobile India.
Two. This is from COMSNETS and Mobile.
Thank you.
And just to inform you, Mobile India starts right away downstairs in Indian Affairs. Thank you again.